Good afternoon, friends. Today we shall be discussing about symmetrical network, symmetrical lattice network. For two-port synthesis. Let us take a simple network function in this form. ZA is an impedance, ZB is this impedance, and similarly you have ZA here and ZB here. Now, what will be for this network? What will be Z11 and Z12 in terms of ZA and ZB? We shall be see the symmetry. We shall be denoting this henceforth by an impedance ZA and ZB. Okay, and it is understood by these dotted lines we denote the other two counterparts. This is ZA and this is ZB. So, we shall be showing only by dotted lines. Now, what will be Z11 and Z12? If you look at this network, see one side is ZA and ZB. So, I can show from one, say I can show it like this, ZA and ZB. Okay. The junction is 1, ZA and ZB. Okay. From ZA, the junction of ZA and ZB, this is 2. There is another branch ZB and ZA. And that junction is 2 dashed. So, basically this is 1 dashed. If you look at it, 1 dashed and 2 dashed, this is a bridge circuit where this potential across the bridge elements will be the output 2 dashed. So, what is Z11? V1 by I1. So, the impedance measured from 1 dashed when this is kept open. So, what is the impedance? ZA plus ZB, again ZA plus ZB. So, it will be ZA plus ZB by 2, this will be Z11. Okay. What would be Z12? Z12 by definition V2 by I1. Okay. So, when current is I1, what is the voltage across this? So, current is I1, this is I1 by 2, this is I1 by 2. So, I1 by 2 into ZA is the drop here. So, from here if I call it V2 2 dashed by I1, what is V2 2 dashed? V2 is V1 minus this I1 by 2 into ZA, is it not? And 2 dashed is V1 minus ZB into I1 by 2. So, that divided by I1. So, that gives me V1 gets cancelled. Okay. ZB, this is minus of this, ZB becomes plus. So, ZB minus ZA by 2, I1 by 2 and I1 by 2. So, ZB minus ZA by 2. So, we have got two interesting results. Z11 is ZA plus ZB by 2 and Z12 is ZB minus ZA by 2. Z22 in this case is same as Z11. Okay. So, if you are given this Z11 and Z12 as the specification, what will be ZA? If I add them, divide by 2, I will get ZB. ZB is this plus this, and ZA is this minus this, Z11 minus Z12. Okay. So, if you are given the specification Z11 and Z12, just subtract Z12 from Z11, you get ZA, add, you get ZB, and hence synthesize. If you are given, instead of this, if you are given in terms of Y parameters, what is Y11? Suppose I call it YA as 1 by ZA, YB as 1 by ZB, then what will be Y11 short circuit parameters? Y11 is I1 by V1 when V2 is 0. So, if I short circuit this, it is ZA plus ZB in parallel, again ZA plus ZB in parallel. So, it will be, and then in series. So, ZA plus ZB, ZA parallel ZB 2 times this. So, twice ZA ZB by ZA plus ZB. Okay. So, if I divide it by this, 2 into 1 by ZA plus 1 by ZB. So, YA plus YB. Okay. So, Y11 is, correct me if I am wrong, YA plus YB into 2 or by 2? Into 2, sure. This is 2 into this, 2 into this. So, this is this all right? 2 by, and what is this? This is parallel combination of So, what is inverse of that? So, this will be YN, YA plus YB divided by 2. Okay. What will be Y12? Similarly, you will find Y12 will be YB minus YA divided by 2. You can verify for yourself. Okay. So, what will be YA? If I multiply by 2 and 2 into Y11 plus 2 into Y12 will be giving me YB, and YA will be Y11 minus Y12, and YB will be Y11 plus Y12, almost identical relationship. All right. So, now the synthesis is very simple, is it not? Compared to ladder network, lattice synthesis is simpler. Now, let us see, there are different types of specifications for two port networks. So, let us synthesize by this method for different specifications. Suppose you are given Z11, let us take an example. Z11 has, let us take an example, Z11 having say LC elements, S cubed plus 4S divided by S squared plus 1 into S squared plus 9, and Z12 is equal to 2S by S squared plus 1 into S squared plus 9. Okay. One thing is you can factorize this, make partial fractions. So, K1S by S squared plus 1 plus K2S by S squared plus 9. Okay. How much is K1? multiply by s square plus 1 divide by s. So, this is s square plus 4. So, 3 by 8, okay, s by s square plus 1. Similarly, this one will be 9, 5 by 8 s by s square plus 9. Okay. Z12 similarly will be say k1s by s square plus 1 plus k2s by s square plus 9. So, that gives me s square plus 1 and divide by s. So, 2 divided by 8. So, 1 by 4 s by s square plus 9. Okay. S square plus 1. Thank you. Then k2, if I multiply by s square plus 9 and cancel out s, so minus 1 by 4 s into s square plus 9. Okay. Now, what will be ZA? ZA was Z11 minus Z12. So, this minus this, okay, I can always write 3 by 8 minus 1 by 4, which is 2 by 8. So, s by s square plus 1 into 1 by 8, okay, plus 5 by 8 minus 1 by 4. So, plus 3 by 8 s by s square plus 9. Okay. So, both are positive real, whereas Z12 may have a negative sign, but you have to see whether after combining everything remains positive or not. ZB, similarly ZB was Z11 plus Z12. Pardon? 5 by 8. Oh yes, minus of ZA. Where did I write ZA? ZA is Z11 minus Z12. So, 3 by 8 minus 1 by 4, okay, 5 by 8 plus 1 by 4. So, 2 by 8, 7 by 8. Thank you. Thank you. Similarly, ZB will be Z11 plus Z12. So, 3 by 8 plus 2 by 8, 5 by 8 s by s square plus 1, and if I add this with this, this will become 3 by 8, okay, s by s square plus 9. So, what does it look like? With this specification, I can realize a network. This is an LC network, LC parallel. A value 1 by 8 Henry, and when S is made very large, 1 by 8 is, that means 8 farads. Is that all right? Again, seven by 72 divided by 8 by 7 farads. Is that all right? This is ZA. Similarly, ZB will be an inductance and a capacitance. These two elements are identical. So, this one will be ZB is 5s by 8s square. So, 8 by 5 farads, okay, and 5 by 8 Henry. Similarly, this one 3s by 8s squared. So, 8 by 3 farads and 3 by 20 3 by 72, okay, Henry. So, these are the element values. there are a large number of elements coming, but network is very easy to realize. Next we go for a situation when Z11 minus Z12, Z11 plus Z12, these things are made. Basically Z12 contributes to the function G12, is it not? It is G12 gain which will be decided by Z12 by Z11. Now I can always multiply this by a constant, because poles and zeros will not get disturbed by that constant. It is something like an amplifier we can put later on, which can take care of whatever gain is to be adjusted. So instead of Z12, sometimes we go for KL times Z12. If I make KL times Z12, then it will be Z11 minus KL times Z12, Z11 plus KL times Z12. Okay. So all these will be multiplied by a factor KL, and we can adjust the value of KL such that every time, whether it is Z11 minus Z12 and Z11 plus Z12, all of them will be positive real, okay, because there may be a negative sign here. So sometimes we will be adding, sometimes we will be subtracting, so some of them may turn out to be negative if we do not have a factor KL. So KL is an adjustable parameter. So G12, this is Z12 by Z11, and we can adjust KL. So we will write KL as a multiplying factor. So for the same problem, for this problem, what is the maximum value of KL, so that we can realize a lattice network? Okay. So we will take up these values now. Z11 is s cubed plus 4s divided by s squared plus 1 into s squared plus 9, which has given me factors like 3 by 8 s by s squared plus 1 plus 5 by 8 s by s square plus 9. We will very soon see the effect of KL, and KL times Z12 will be KL times 1 by 4 KL by 4 s into s square plus 1, okay, minus KL by 4 s into s square plus 9. Okay. So ZA is Z11 minus this, so 3 by 8 minus KL by 4 into s by s square plus 1 plus 5 by 8 plus KL by 4, okay, into s by s square plus 9. ZB will be 3 by 8 plus KL by 4 into s by s square plus 1 plus 5 by 8 minus KL by 4 s by s square plus 9. Now for this to be positive real, what should be the range of KL? KL you vary from say minus to plus. If you vary, then this has to be always positive. So 3 by 8 is equal to KL by 4, that is the limiting situation, when this becomes KL is equal to 3 by 2. Okay. If KL becomes more than that, then this will become negative. So KL should be less than equal to 3 by 2, and here KL by 4 I can take it to minus 5 by 8, till that time it will be positive. That means minus 5 by 2, minus 5 by 2 less than KL. So these are the two limits for KL, for ZA to be positive real. Similarly for ZB, it will be minus 3 by 2 KL and 5 by 2. Now, if you use both the restrictions, then KL should be minus 3 by 2 to plus 3 by 2. Okay. So, you can choose any of these limiting values and then see what will be the network like. Suppose we choose KL is equal to 3 by 2. Let us choose KL equal to 3 by 2 plus 3 by 2. Then what happens? If we choose KL equal to plus 3 by 2, first term becomes 0. So, this element will not figure in ZA. Only thing, accordingly this value will change. So, 3 by 2, 3 by 8 plus 5 by 8. So, ZA is equal to S by S squared plus 9. Is that so? 3 by 8 plus 5 by 8. ZB in that case becomes 3 by 2 means 3 by 2. So, 3 by 8 plus 3 by 8, 6 by 8, 3 by 4, okay, 3 by 4 S by S square plus 1, and this one 5 by 8 minus 3 by 8. So, 1/4, 1 by 4 S by S square plus 9. So, in ZA you have just one LC network, in ZB you have two such elements. Is that all right? You can calculate their values. Okay. See, earlier we had one parallel bank here, again another tank circuit here. So, this one again here a similar element will be coming. So, these we are eliminating by taking KL equal to that limiting value, one of the limits. If you take KL equal to the other limit minus 3 by 2, then in ZB this will get eliminated. So, ZB will have one less element, alright, whereas ZA will have two elements. So, this is how you realize the networks for ZA and ZB. Let us take another example. Okay, let us take another specification. ZA and ZB, we have seen the specifications in terms of G12, Z11 and Z12, and G12 with a gain factor KL. Okay. Now, if you are given only G12, if you are given only G12, if only G12 is specified, only G12 specification means you are okay. Z12 is how much? Half of ZB minus ZA, and Z11 is half of ZB plus ZA. Okay. Or twice this equal to this, and twice Z11 is equal to this. Suppose we are specified, let us come to G12 specifications just a little later. If only Z12 is specified, if you are given only Z12, then I can always adjust ZB and ZA in such a way that ZB minus ZA corresponds to Z12, and both ZB and ZA are positive real functions. Okay. You can have ZB and ZA as positive real functions. So, Z12 you are given say 3 s squared plus 6s plus 1. Mind you, Z12 need not be a positive real function, divided by s plus 1 into s plus 2 into s plus 3. Okay. So, we write twice Z12 as this. It is the twice Z12 which is specified. So, break it up, s plus 1, what is it? Minus 1 by s plus 1 plus s plus 2, if I write minus 1 by s plus 2, s plus 3, how much is it? S plus 3, 5 by s plus 3. Okay. You can see s plus 1, if I make s plus 1 equal to 0 or s is equal to minus 1. So, 3 into 1 minus 6 plus 1. So, 3 plus 1 4 minus 6 minus 2 divided by 1 into 2, alright. So, that gives me minus 1 by s plus 1. Similarly, this one. So, this is equal to ZB by ZB minus ZA. So, since this is with a minus sign is with ZA, so this I can put in ZA, this I can put in ZA, this in ZB. So, ZB I can always choose as 5 by s plus 3, so simple, and ZA as 1 by s plus 1 plus 1 by s plus 2. 5 by s plus 3 1/5 farad and 5 by 3 ohm resistance, and here 1 by s plus 1 is 1 farad with 1 ohm resistance, 1 by s plus 2 with half ohm resistance, 1 farad with half ohm resistance. So, this is ZA and ZB. Okay. So, if you are given only this specification, it is very simple, you can choose any value of ZA and ZB. Next, ZA by ZB I can calculate. See, what is G12? G12 is Z12 by Z11, and Z12 in terms of ZA and ZB is ZB minus ZA divided by 2, will get cancelled, ZB plus ZA. Okay. So, from there if I make component dividendo, this will become 1 minus G12 by 1 plus G12. Okay. If G12 is given as some PS by QS, then it will be PS plus, sorry, QS minus PUS, QS minus PS divided by QS plus PS. Okay. So, depending on the nature of this 1 minus G12, sometimes ZA may match with this, ZB may match with this, or ZA may match with 1 by this, and ZB may be 1 by 1 minus G12. So, one may choose ZA as 1 minus G12 if it is a positive real function, or ZA as 1 by 1 minus G12 and ZB, sorry, 1 by 1 plus G12 and ZB as 1 by 1 minus G12. Okay. Suppose when you write G12 as PS by QS, ZA by ZB you write like this, and we get this as an even part plus an odd part. Similarly, even part and an odd part. If it so happens either M1 M2 is a constant or N1 by N2 is a constant. That means either the odd part or the even part of the numerator is a constant times the corresponding part of the denominator, or the even part of the numerator is a constant times the even part of the denominator. Then something very interesting comes. ZA by ZB, I can write this as 1 plus N1 by M1 divided by 1 plus K times N2 is K times N1 by M2. Okay. So, this is odd by even, this can be an LC network, this is also odd by even, another LC network. This is a resistance, this is a resistance. So, it will be like this, a resistance and an LC network, series inductance, series parallel inductance capacitance. Similarly, this side you will have a resistance and similarly another LC network. I could have done it the other way around also. If M1 is some constant times M2 or M2 is constant times M1, I can divide it by N1, sorry, that is what we have done. If N1 and N2 they bear this relation, I made a mistake, sorry, correct. Okay. So, I can get a similar expression. So, let us take one example. G12s is equal to S squared plus 1 by S squared plus 5s plus 4. Okay. So, Qs plus minus Ps will be S square plus 5s plus 4 plus minus S square plus 1, which gives me there will be two polynomials. So, ZA by ZB, ZA by ZB will be, first is the negative. So, S square will go 5s, okay, plus 3 divided by twice S squared plus 5s plus 5. Okay. So, if you separate out the even part and the odd part, 3 plus 5s divided by 2s square plus 5 plus 5s. So, these two are constant, I mean proportional, ratio is 1. So, divide throughout by 5s. So, I can write this as 1 plus 3 by 5s divided by 1 plus 2s square plus 5 by 5s. Okay. So, ZA I can write as 1 ohm resistance plus 3 by 5s. So, 1 ohm resistance and a capacitor of 5 by 3 Henry Farad, and ZB as 1 ohm and then 2 square plus 5. So, it is an LC parallel combination. Okay. We can find out the values of L and C. ZB is 1 plus 2s square plus 5 by 5s. So, it is basically a series combination. So, L and C, sorry, this is the series combination. Okay. Let us take up one or two more examples. It will be easier to follow. Let us take this problem. Z12 is equal to 3s squared plus 5s plus 1 divided by S plus 2 into S plus 3 into S plus 5. So, how do you find out the lattice network? It is simple. Z12 we have seen ZB minus ZA. So, let us break it up into partial fractions. K1, K2, K3. Sorry, S plus 3. Ready. Similarly, S plus 5, 25 into 3, 75 minus 5 into 5, 25. So, 50, 51, okay, divided by 3 into 2, 6. So, this is 19 by 2. Okay. So, what should be ZA? ZB minus ZA is Z12, is it? Z12 is how much? Twice or twice Z12. So, twice Z12 we will have to calculate is 2 times this, 2 by S plus 2 minus 13 by S plus 3 plus 19 by S plus 5. So, ZA and ZB will correspond to this 2 by S plus 2, okay, plus 19 by S plus 5, we can put it this way, and ZA is whatever is associated with the negative sign, 13 by S plus 3. Okay. So, 2 by S plus 2 is an RL network or RC, sorry, RC of value 1 ohm and half a farad, and then again so this is 1 by 19 and 19 by 5, okay, and this side ZA 13 by S plus 3. So, 13 by 3 ohms and 1 by 13 farad. So, this will be the lattice. We are given another example. G12 is equal to S squared minus 4 by S squared plus 4. Okay. So, what is ZB by ZA or ZA by ZB? How much is that? ZA by ZB, this minus this, 4 by S square. Is that all right? 8 by twice S squared, 4 by S squared. So, what should we take? ZA I can write as 4 by S and ZB as S. So, you have ZA as a capacitor of 1 by 4 farad and ZB as an inductor 1 Henry. Or in other words, you are having a capacitor and an inductor and a capacitor. Is it all right? 1 Henry and 1/4 farad. So, for this network the gain function will be this. It is a very interesting distribution. Okay. Now, this is the basic background that I have given for 2-port lattice synthesis. Now, we have normally the impedance, the networks will not be necessarily terminated by infinite impedance, they can be terminated by a fixed impedance. Sometimes they are terminated by fixed impedance. So, if they are terminated by a fixed impedance, what is that relationship between output and input? That is, for a terminated network which is terminated by a constant resistance R, not in this example, you have a 2-port network, and if we have a terminating resistance R, then what will be the relationship between input and output? Okay. Let us take the original relationship between voltages and currents. V1 is equal to Z11 I1 plus Z12 I2, and V2 is equal to Z12 I1 plus Z22 I2. This is the general relationship. When it is terminated by a resistance R, then V2 is also equal to minus I2 times R. All right. Conventionally, we take the currents to be positive when they are inward, but when I am terminating it, then I2 is in the negative direction. So, V2 becomes minus I2 into R. Okay. So, what will be the impedance seen from this side 1 dashed? I call it ZS. Impedance seen from this side, that is V1 by I1 when this is terminated. So, let us substitute it here, minus I2 into R is equal to Z12 I1 plus Z22 I2. If I take I2 on this side, then minus Z22 plus R into I2 is Z12 I1. Pardon? 1 2 and Z22 I2. See, I am taking this equation, this is equated to this. So, minus I2R is Z12, Z12 and Z21 they are identical. That we have seen for passive bilateral network, it is same. Okay. So, I2 I can write as Z12 by Z22 plus R into I1. Substitute this in the first equation, what do you get? V1 is equal to Z11 plus Z12 into I2, which is Z12 squared divided by Z22 plus R whole thing into I1. Okay. So, ZS, which is V1 by I1, V1 by I1 is nothing but Z11. If I multiply Z11 Z22 plus Z11 R plus Z12 squared whole thing divided by Z22 plus R. Okay. If we make R is equal to 1 ohm, if we find that in a normalized situation if R is 1 ohm and the impedance seen from this side is also 1 ohm, then what happens? If V1 by I1 is also 1 ohm, so Zs is equal to 1 ohm, when R is 1, what do we get? Z11 V1 by I1 is equal to Z11 plus Z12 squared by Z22 plus 1 equal to 1, or Z11 Z22 plus Z11 plus Z12 squared is equal to Z22 plus 1. Am I all right? So, what do you get? Z11 into Z22 plus, now if we have a symmetrical network, then Z11 is equal to Z22. Okay? Is it all right? So, Z11 and Z22 they are same. So, this is Z11 squared plus there is something I have made a slip, Z11 squared, just check up. There was a negative sign somewhere. So, I2 was negative. So, this one will be Z11 minus Z12 squared. Is that all right? Sometimes such mistakes will put you to a challenge when you do not get the desired result. So, minus Z12 squared, or Z11 squared is equal to 1 plus Z12 squared. Okay. What is Z11? ZB plus ZA by 2. What is Z12? ZB minus ZA by 2. If I substitute here Z11 squared, that is ZB plus ZA by 4 is equal to 1 plus ZB minus ZA squared by 4. Equate ZA square ZB square will get cancelled. So, you are left with twice ZA ZB. So, ZA ZB by 2. Okay. If I bring it to this side, then A plus B whole square minus A minus B whole square, that will be 4AB. That divided by 4 is just AB. Okay, thank you. ZA ZB comes out to be therefore 1. So, if you want that the network, we are planning to have a network which, if terminated by a resistance R, let us take a normalized situation 1 ohm, then the impedance in from this side is also 1 ohm. What will be that ZA and ZB? Now, ZA and ZB must be at this relation, ZA ZB is equal to 1. So, in the next class we will start from here. This is for a normalized relation. If it is equal to any R, ZA ZB should be equal to R squared. So, ZA ZB should be equal to R squared. That you can see from here itself. If you would have put R here, would have got R squared. So, in general ZA ZB should be equal to R squared. So, once you select ZA, automatically ZB is fixed. For such lattice network, terminating impedance R will generate an impedance of R from the looking inside. Thank you very much. afternoon, friends. Today we shall be taking up Fourier series. So far we have discussed about network functions and their behavior under different conditions with the different types of excitation. For example, a ramp or a step or an impulse or a sinusoid. Like this, we have taken up different types of functions and we have seen the behavior of networks, and we have used so far in the time domain the response has been evaluated by using Laplace transform. Okay. Suppose you are given a network and you have a periodic function. Then you take the Laplace transform of this, take the network function, and then you can evaluate the response. So the response will also be periodic or something like this. Now, the response that we get taking Laplace transform of the function is giving me a total solution, that is, say total solution means including the transients. Suppose the response is like this. After some time it will be stabilizing to a steady value. If you are interested in getting the steady state solution, we are not interested in the transient part, we are interested only in the steady state solution. Then there is an advantage of using the frequency response technique. We have studied so far the response due to a particular frequency. Okay. Now, if you are giving a periodic function, I would say of this type, if you are giving a periodic function as input, is it possible to resolve this into large number of sinusoidal functions? Our aim here is to resolve that and then find out the response corresponding to each elementary component of those functions, sinusoidal functions, and the response due to each one of them you calculate independently, then use superposition theorem, take the total sum, that will be the response due to any periodic function. So, for periodic power signals, we mean power signal means signals with finite average power. Suppose x t is a function which is given as a in this range and t by 2, t and t, that means this is a kind of function. We define periodic functions only in one period, that is good enough. Like this. Okay. This is 0, t by 2, t, 3t by 2 and so on, this is minus t by 2 and so on. What will be the Fourier coefficients for such a function? Am will be 2 by t0, 0 to, okay, we can write 0 to t by 2, a, this magnitude is a, into cosine m omega naught t dt, minus plus t by 2 to t that this becomes minus a cosine m omega naught t dt. If you integrate 2a by t naught will come as a constant and here you get sine of m omega naught t by m omega naught 0 to t by 2, then with a negative sign sine m omega naught t by m omega naught t by 2 to t between 0 and 5. So, it will be 4 by t 0 to t by 2, that function f t and sine n omega naught t, where n is odd, and similarly this is Bn, and An will be similarly 4 by t 0 to t by 2 f t cosine n omega naught t. Okay. If you take n even, then what happens? Let us see. Now, you are having between here this and this point, say something like double harmonic. Here you see this is one period, this is positive and positive, but here it is negative and positive. This is negative, but this is a large value and this is this much value. Its counterpart is here, where both are negative. See, this component, the product of this part, this zone is equal in magnitude to the product of this, but here it is positive into negative, here it is negative into negative. So, they will be cancelling. So, this is an odd function. So, if n is even, product is odd, this product is odd, and hence the integral is 0. Okay. So, a n and b n will be 0 for n even for this type of half wave symmetric function. All right. So, thank you very much. In the next class, we shall be continuing with this, a few more interesting features of Fourier series and some standard functions we will take for evaluating the Fourier series. Thank you.